K. Paranivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on chemistry of environment. We are discussing about fundamental aspects of chemistry, and today lecture we are going to discuss about thermodynamics aspect of chemical reactions. So the thermodynamics and kinetics are very important two aspects for any chemical reactions, and we should know what are the thermodynamics aspects of the particular chemical reaction involved in the environmental aspects. The other one is kinetics aspects. So first, today we will discuss about thermodynamics aspects of various chemical reaction. So the thermodynamics actually is a study of energy changes accompanying in a chemical process, and this actually is a relationship between the heat involved in a particular chemical reaction and the work done actually. Okay. So that is the energy changes, heat and work done in a particular chemical reactions is dealt with this thermodynamics. So whenever there is an interaction between energy and matter, thermodynamics is involved. Whatever the reaction, energy is there and matter is involved, definitely thermodynamics has to be there. Some of the examples include heating and air conditioning system, refrigerator, water heater. In all those things, thermodynamics is involved. So the analysis of thermal system is actually achieved through the application of conservation of mass as well as conservation of energy. Both are important, mass and energy conservation, and that comes under the thermodynamics aspects of this particular chemical reaction. And really the energy is viewed as the ability of the particular system to cause changes. So the energy involved in a particular chemical reaction goes with this, and that is actually responsible for causing the changes, that is from reactants into products. And thermodynamic systems are classified as either closed system or an open system. The open system means it can exchange mass and energy with the surroundings, whether in the closed system it is not possible. Let's see some of the properties of a particular system. Any characteristics of a particular system is called a property of the particular one. In the conventional classical thermodynamics, the substance is assumed to be a continuum, homogeneous matter with no microscopic holes in the particular thermodynamic system. And this assumption holds as long as the volume, length scale are large with respect to the intermolecular spacing. That is, the assumption has to be there in the particular system we are considering the thermodynamics aspects. And coming to the properties, there are two types of properties deals with the system. One is intensive properties, the other one is extensive properties. And the intensive properties are those that are dependent of the size of the system. Independent of the size of the mass of the system. That is such as temperature, pressure, density are the parameters example for intensive property, and they are not additive. For example, temperature, if we measure 1 liter or 10 liter of a particular water body is going to be the same. And similarly, if we measure a pressure of the system, whether it is small or large, it is not matters. Okay, so such type of properties representing a thermodynamics aspects is called intensive property. It is independent of the mass of the system or the size of the system. Whereas extensive properties, if you look at it really, these values are that depend on size of the system, such as mass, volume, and total energy represented by U. So it depends on what is the mass of the system. Accordingly, the properties will vary, and they are additive in nature. A thermodynamic system can be classified as intensive properties or extensive properties. In thermodynamics, what is important, especially for a particular reaction taking place, and we should know a particular reaction is spontaneous process or not, or a particular reaction is feasible or not, that is from environmental angle, that is very, very important. A particular reaction can proceed without any outside intervention. So such type of process, that is a process which can take place by itself, or it has a tendency to take place. So such processes are called spontaneous process, that is, it is feasible. And the processes that are spontaneous in one direction are non-spontaneous in the reverse direction. So this is an example as melting of ice. It will go only one direction. Okay? Otherwise, we have to spend more energy to reverse it, all this. All spontaneous processes are usually irreversible. What is a reversible and irreversible process? A reversible process means the original state of the system and the surroundings can be restored by reversing the changes. So such a type of reactions or processes called reversible. Irreversible process means the system cannot return its original state by reversing the changes. So a chemical reaction can be grouped into a reversible or irreversible process. There again, the thermodynamics values will help you to predict a process is spontaneous or not. In this thermodynamic process, a particular system undergoes, let us assume, a thermodynamic process which changes when there is some sort of energetic change within the system, and generally associated with the changes in parameters like pressure, volume, internal energy like temperature, or any sort of heat transfer. In all these processes concerning the thermodynamic one, there are several specific type of thermodynamic process that have special properties. Okay? Depending on how it is happening, these thermodynamic processes are grouped as below and named accordingly. It depends on what are the heat relevant to that, what are the volume, what are the pressure, and what are the temperature. Accordingly, the thermodynamic processes are classified as, first one is adiabatic process. So a process in this with no heat transfer into out of the system. So such type of processes are called adiabatic process, that is, no heat transfer involved in the particular chemical reaction or the system. Isochoric process means a process with no change in volume, that is, in which case the system does not actually work, is called isochoric process. The other one is isobaric process, that is, a process with no change in pressure involved is called isobaric process. And very importantly, directly with the temperature connection, is isothermal process, that is, a process with no change in temperature is called isothermal process. So the starting from A to B involves no change in temperature. Both A and B are in the same temperature. So depending on whether any heat is involved or no heat, change in volume involved or no, and no change in pressure, no change in temperature, these processes are called isothermal, isobaric, isochoric, and adiabatic process of thermodynamic processes. And there are different laws concerning thermodynamics. We should see some of the things. What is that? One common law deals with equilibrium is called zeroth law of thermodynamics. Suppose two bodies in thermal contact with a third body which will be at the same temperature. Okay? So there are three systems, A and C, or A and B and C, and out of this three, two are in contact and there is a thermal equilibrium, and if they are in contact, the third body also, they will also be in same temperature. This is called zeroth law of thermodynamics. That is, two bodies in thermal contact with a third body, okay, will be at the same temperature. This is deals with temperature equilibrium, that is known as zeroth law. Apart from this, we have first law and second law of thermodynamics, which is also relevant to environmental applications. The first law of thermodynamics is a very popular one. It deals with conservation of energy. Okay? So energy cannot be created nor destroyed. This is a statement, and that is the first law of thermodynamics, which clearly says the conservation of energy in a system. So it simply states that during an interaction, energy can change from one form to another, but the total amount of the energy remains constant in a particular system. So this is what represented by chemical equation delta E, change in energy, that is energy of the final system minus energy of the initial system. That's called change in energy, delta E. And this is also as per the first law of thermodynamics, delta E is equivalent to Q plus W, that is work done and quantity of heat. So this is the thermodynamics first law statement, and these are the corresponding equation. When we come to the second law of thermodynamics, and here again there are two concepts. One is energy, the other one is entropy of the thermodynamic system. The energy has quality as well as quantity, and the actual process occur in the direction of decreasing quality of the energy. So this is a second law of thermodynamics statement. When we come to entropy, represented by S, the entropy of the universe does not change for reversible process, and in the case of irreversible process, it is increases. That is, for spontaneous processes, the entropy of the system is increasing. This is a second law of thermodynamics, that is deals with the entropy. The entropy of the universe does not change for reversible process and increases for spontaneous process. So these are the laws actually dealing with thermodynamics aspects. When we see some more aspects of entropy, that is, energy can be thought of as a measure of the randomness or system of a system. That is, entropy is a measure of disorder, that is represented by delta S, that is equivalent to Q, that's a heat content of the reversible process divided by temperature of the system. Entropy, change in entropy is equivalent to this equation. So entropy is nothing but measure of disorder of a particular system. Entropy of a substance is minimum in solid form, while it is maximum in gaseous state. Okay? Because gaseous molecule always will have interaction, whereas solid state it is minimum. So as per this definition, solid materials having minimum entropy value, whereas gaseous state will have a maximum entropy value. Like internal energy, that is E, the enthalpy, heat content of the system, entropy is a state function. Therefore, it depends on how it was brought out is immaterial, what are the entropy, the initial and final alone sufficient. So these type of system like energy, enthalpy, entropy also a state function. How it was brought out from the initial state to final is immaterial. It depends on entropy of the initial and final value. And in the case of a reversible process, that's a change in entropy of the universe is equivalent to change of the entropy in the system plus change in the entropy of the surrounding is equivalent to 0. Okay? So this is a case for reversible process. Both the system as well as surroundings, if you put it, the change in entropy value is equivalent to 0. This is true for a reversible process. Whereas in the case of a real or spontaneous process, that is entropy, change in entropy of the universe is equivalent to change in the entropy of the system plus change in the entropy value of the surroundings is always higher. that is greater than 0. This is true for irreversible process. So entropy change in the universe, that is composed of the system and the surroundings. Therefore, change in entropy in universe is equivalent to change in the entropy of the system plus surrounding. And for spontaneous process, the change in entropy of the universe is always greater than 0. Another important thermodynamic parameter is enthalpy, usually represented by the term H. It is defined as a total heat content of the system, and it is equal to sum of the internal energy and pressure volume work. So mathematically it can be represented as H, that is equivalent to U, that's the internal energy, so represented by E, that is equivalent, plus P into B, that is pressure into volume. This is actually known as enthalpy of the system. So change in enthalpy, represented by delta H, is a heat absorbed or evolved by the system at constant pressure. So heat may be liberated or absorbed in a particular system at constant pressure. That's called change in enthalpy. And for exothermic reaction and endothermic values, it varies. Okay. Exothermic reaction means, always we know, it's liberate heat. Heat is given out into the surrounding. There will be a liberation of heat in the exothermic reaction, that is delta H and Q both are negative value. For endothermic reaction, that is system absorb energy from the surrounding, and here the delta H and Q value both are positive for endothermic reaction. For example, endothermic reaction, if you dissolve potassium chloride or glucose in water, if you touch the glass, it will be chilled, cool. That means heat is taken up by the system when it goes into the solution. This is an example for endothermic. Exothermic, suppose it dissolve lime, calcium oxide in water, that liberates heat. So example for exothermic, if you dissolve calcium oxide in water, liberates heat, whereas if you dissolve glucose or potassium chloride, it absorbs heat and goes into the solution. So exothermic reaction releases energy into the surrounding from the system that is always hot surrounding, whereas endothermic reactions absorb energy from the surrounding, that is the form of heat, and actually the surroundings will be cold. If you touch it, we can see this. Okay, this is a exothermic, this is a endothermic, goes into the system, that is dissolution of some kind of salt in water. So this is thermodynamic potential. Also you can see here how the behavior for exothermic reaction and the situation for endothermic reaction you can see here. Okay, it is a reverse of this. The chemical potential diagram indicates how it is differs for in the case of exothermic and endothermic reactions. Another important term in thermodynamics which is relevant to environmental field is Gibbs energy. It's also known as free energy or Gibbs energy. The scientist involved is a Gibbs, so it is normally represented by the term capital G. And it is the energy available in a system to do useful work and is different from the total energy change of a particular chemical reaction. And the Gibbs free energy is a chemical potential energy in a particular substance, and it is given by this chemical equation G, that is equivalent to H enthalpy of the system minus T, that is a temperature multiplied by the entropy value of the system. So this is actually the Gibbs energy. It depends on enthalpy and entropy plus temperature of the system. So in this equation, G represents a Gibbs energy, H is the enthalpy, T is the temperature, and S is the entropy. The enthalpy and entropy are the thermodynamic properties of a particular system related to the system internal energy and its degree of disorder. The free energy is one of the most important thermodynamic function for the characterization of the system. If you know this value, we can characterize the system thoroughly. And it is a factor in determining outcomes such as the voltage of an electrochemical cell and the equilibrium constant for a particular reversible reaction, etc. We can get information about the free energy or the spontaneity of the particular reaction. It can be change in the value delta G, actually measured by the change in the enthalpy as well as the entropy of the system, and the relationship is given here. So in this, the delta G is a symbol for spontaneity, and there are two factors which can affect the enthalpy and entropy of this value. The enthalpy, that's the heat content of the system at a constant pressure, and the entropy, the amount of disorder in the particular system, it's under control. When the delta G value is greater than 0, it is a non-spontaneous reaction. Okay? And when the delta G value is negative or less than 0, that is a spontaneous reaction. So this is in reverse to the what we discussed about change in the entropy value. So any reaction to take place spontaneously, or a particular reaction is feasible or not, based on this delta G value, we can come to a conclusion. Okay? If the delta G value, that is change in free energy content from the initial to final system, is positive, then that particular reaction may not take place, or the particular reaction is non-spontaneous. Suppose the delta G value is going to decrease, that is a negative value, then the reaction is feasible, or the particular reaction is spontaneous in nature. So the spontaneity of a particular reaction can be information from this Gibbs free energy. So in chemical transformation, chemicals always want to minimize their Gibbs free energy. So all the chemicals, they try to minimize the free energy of the system. So chemicals will tend to transform to other state, or chemicals that have less Gibbs free energy. That is what the spontaneity of the any particular system. For example, the rock, if not supported by the rope, will always want to fall off the ground where it has less potential energy. And a chemical with a higher Gibbs free energy will always want to transform to a chemical with a lower Gibbs free energy. So this is what spontaneity of the particular reactions happening. And these type of chemical reactions are called spontaneous reactions, because they happen without the need of an energy input, and we want to reverse it, then we have to supply energy. Okay? That is not natural. Okay? So for any chemical particular reaction, the delta G value will give you whether the reaction will take place spontaneously or not. We can, by measuring the delta G value indirectly from the enthalpy and entropy value, we can get information about the system. And really, if you look at the relationship between the free energy and the equilibrium constant value in a particular reaction, we can get information. Generally, as we discussed before, the free energy is negative, the reaction will take place spontaneously. That is also related with equilibrium constant for a particular chemical reaction as per this equation or the modified equation. So the equilibrium constant, generally the equilibrium constant value is very high, then that particular reaction can take place spontaneously. Okay? That is also supported if the more negative value, that is the minus sign here in this equation indicate the equilibrium constant value is very high, then the spontaneity of the reaction will take place very rapidly. So this delta G value is also related to the equilibrium constant equation based on this one. So when equilibrium is attained, there is no further energy changes, that is the delta G value is 0, and the equilibrium constant value, that is 1, hence the above equation becomes simplified. The previous equation will reduce to this form, and thus the delta G naught is nothing but minus 2.3003 into RT into log K value equilibrium constant for the particular chemical reaction. So, the rule here is, if the equilibrium constant value is high, definitely again spontaneous or the particular reaction is feasible, that is also supported by the G value, that will be more negative. The G value is also related to the electrochemical cell potential taking place in galvanic reactions. So, in the case of galvanic cell represented by the electrochemical cell, the Gibbs free energy change, that is delta G, is related to the electrical work done by the cell, and normally represented by this equation. Delta G is equivalent to minus NFE. Number of moles involved, F is the Faraday's constant, and E is the electromotive force of the cell, that is a cell potential. So, this equation also clearly indicates, if the value of E, electromotive force of the particular cell, is positive, then the reaction will take place spontaneously, because this value is positive and you can see the minus sign here. So, that means the delta G value will be more negative. So, if reactant and products in the standard state is in the standard condition, delta G naught is equivalent to minus NFE naught. This is a standard electrode potential for any hydrogen cell with a represented by H plus at 1 atmospheric pressure and hydrogen, that is called E naught value is 0. So, that is taken as a standard one. It depends on the oxidation and reducing species, the E naught value will vary. For hydrogen it is 0. So, any system which is governed by oxidation and reduction, and that is also governed by the galvanic cell features, in the E value, that is the electromotive force positive value, definitely that reaction will take place spontaneously. That is, the oxidation and reduction reaction will take place spontaneously in converting the electrons from one part to another part, will take place spontaneously. Suppose the E value is negative, then the reaction is not spontaneous. This also clearly says, if it is a E value is positive, the delta G value will be more negative, then the particular reaction will take place spontaneously. So, to sum up, the thermodynamic parameters also very important in environmental field, like entropy, enthalpy and free energy. All the three terms in turn are related to the work, also the electrochemical reactions, the standard electrode potential, and the chemical equilibrium reaction, the formation constant or equilibrium constant value. That tells you a particular reaction is feasible or not, or spontaneous or not, based on this. To sum up, if the values of electrochemical cell is positive, the reaction will take place spontaneously. Similarly, the equilibrium constant value is very high, then also it will take place spontaneously, and that is accompanied by decrease in free energy from the initial system to final system. Thank you.